Now we will look at dividing rational expressions. And so the first example I'd like to look at is I'd like to look at a numeric example. I have 4 over 25 divided by negative 6 over 5. The deal is, if you ever see division of fractions, you may remember this, is you want to flip the second one and multiply. So dividing is actually the same as multiplying by the reciprocal of the denominator. Why is that? I think we get that question a lot. I think it's good to look at the why a little bit sometimes and really wonder why is that happening. So let's actually look at this one really quick and do the why. Now you won't have to do this when you do your problems. Just remember, first one's lazy, second one's crazy. It flips over and changes from division to multiplication. Then you're just basically at a multiplication problem. But the why behind it, it's 4 over 25. Basically, if I was to write it out as division, it's negative 6 over 5. I could use a big division bar like that, right? It means the same thing as the division bar here. I'm just writing 4 over 25 divided by negative 6 fifths. But this is called a complex fraction. You have a fraction within a fraction. It's messy. You don't usually want that. So to get rid of that, multiply by the reciprocal of the denominator, and that's going to cancel out. But anytime you take a fraction, you multiply a number to the bottom to keep it equivalent. You have to multiply the same number to the top. So these, any number times its reciprocal is always 1 because they cross cancel. Everything cancels out. You get 1 over 1. And so that's why when you're looking at dividing fractions, they're the same as multiplying by the reciprocal. So I know I can just use this. This is basically changing to multiply this by negative 5 over 6. Now I'm just going to treat it like we did last section. I can go, cool, 5 goes into 5 once, 25 5 times, 2 goes into 4 twice, goes into 6 3 times. I can multiply straight across. Positive times a negative, I'm going to end up with a negative 2 over 15. And that's all I have to do for this type of a problem. Now that's a numeric example. Now I put up a pretty tricky one here. It's going to hit on a lot of little different things that you may see depending on whatever textbook you're using. So in this case, in our textbook, they're really, the one that we have for this course now, the author's really big on this whole factoring out a negative 1 thing. So that's why I put something like that in here. But anyways, I treat it the same way. I'm thinking this is just a multiplication problem. So I think, okay, for now that's factored. Factor everything I can. And I'm sorry, before I do that, I would like to just rewrite it as the multiplication problem first, just so I don't get that mixed up. So let me change this to times. And then I'm going to put 2x squared minus 12x plus 18 over x squared minus 4x plus 3. So I basically, first one's lazy, second one's crazy, changes the multiplication, second one flips over. Now I'm going to factor everything in it, just like we did in the multiplication section. That's what we have to do. And we're going to start canceling, dividing things out. We could factor these like we did before too, this 5 times 5, and canceling the common factors. That's what I'm going to do here, factor everything. So in this one, I see that 2 comes out of this. I'm left with an x squared minus 9. That can even factor further. And this one right here, I'm gonna leave this one for now because there's a little trick to this one. And this one right here, I notice there's a 2 that can come out as a GCF, and I'm left with x squared minus 6x plus 9. And then the next thing underneath there, that's binomial times binomial, x and x. What multiplies to be positive 3 adds to be negative 4 will be negative 3, negative 1. Now I've noticed that I have an x minus 1 here, and this is 1 minus x. Well, the deal is you can factor 1 or negative 1 out of anything, and so some textbooks are really big on this and they throw it in like every other problem. But if I ever see that and I see the signs are just switched, I can actually just take out a negative 1, and then it just becomes x minus 1. It flips it. Basically, if you factor a negative 1 out of this, if I remultiplied this, I'd get negative 1 times x is negative x. Negative 1 times negative 1 is positive 1. So you can actually put that negative 1 to make these the same binomial. So let me erase this here now. So now we can take this and we are down to, let's factor it completely now and start doing our canceling. And this ends up being x and x. Looks like it's -3 and -3, right? Multiplies to being positive 9, adds to be -6. And then down here, we already had this as x -3, x -1. What did we factor this to? Actually, difference two squares yet. X plus 3, x -3. What's being squared in the front goes in the front. What's being squared in the back goes in the back. So now I have this thing all factored. Let's start canceling stuff. I know I just did the quick division way on this one, but really they could have wrote as 5 times 5, like I mentioned, and cancel the 5s, and 2 times 2, and 2 times 3, and cancel the 2s. That's really what we're going to do. That's what we're doing here with this stuff, is cancel out my x -1 3s. They're gone. Let's cancel out my x -1s. Gone. Cool. We got 2s that cancel out. There's a lot of stuff canceling out. X -3 again is going to cancel out here. Anything on top with anything on bottom. Now, all I see left on top is just a -1. On the bottom, I just see an x plus 3. So really, my final answer, the whole fraction, is be -1 all over x plus 3. And that's it. So that's an example of dividing rational expressions. Attack them all the same way. Essentially, multiply by the reciprocal, factor everything, cancel common factors, multiply straight across.